The simplest line I can think of is a straight line. Straight lines are described by linear equations either in the form of y equals mx plus b or a1x plus a2y equals a3. You'll see both of these forms in different applications of linear equations. The one we're going to focus on in this video is y equals mx plus b, so we can focus on some of the properties of linear equations. Now, linear equations are introduced in an algebra class, but they're often used in engineering applications to simplify the complex behavior of a system or a relationship between parameters in a linear form. And so we'll look at what that means briefly in this video, and in future videos we'll look at problems to solve for different aspects of this linear equation and different applications of linear equations. Let's first remind ourselves of the different properties of a 2D graph. We have a horizontal axis, oftentimes represented as your x-axis, where going to the left you get a smaller value, and this goes all the way to infinity, so negative x direction here to the left. To the right, your value of x grows larger and larger, in this case positive x. This is our horizontal axis. In a 2D graph, we also have a vertical axis. Vertical axis is represented usually by a positive y pointing up and a negative y pointing down. We split the axes into little grid components and assign them values. So here we have the x-axis going from -10 all the way to +10. Here we have the center as 0. Vertical axis, we can do the same thing, going from -10 to +10. But recognizing that the arrows represent that values of y and x go beyond the values shown here, right? It goes all the way to infinity. It's often useful to throw this on a graphing paper of some kind, a grid of some kind, so you can easily identify at different locations what the point is. So we can draw points, and the convention is naming the point as x comma y. So where you see my laser pointer right there, this would be the 6,6 point. If I place it, let's say here, this would be x equals 4, y equals 9, so 4,9. And so we represent our points that way. A very useful point to recognize and relate other points to is the origin. Origin is the 0, 0 value. Now, it is conventional to draw the axis where it crosses at the origin, like it's shown here, but there's no rule. We can move these axes to different sides depending on what you're actually looking for, or you might just show part of these axes. Depends completely on the application you're looking at. When we draw the axes and cross them at the origin, we split the graph into 4 distinct quadrants. The quadrants are defined by the signs of x and y. In this first quadrant, you see only positive x and positive y values. Any point here will have a positive x and positive y value. In this second quadrant, in the top left, you see that you have x values that are negative and y values that are positive. So any point in here will have a negative x and positive y value. In this bottom left third quadrant, we only have negative x and negative y values, and the bottom right fourth quadrant, we only have positive x and negative y values. This becomes very important in describing and understanding linear equations as well as any other kind of equations. Knowing where we are in the quadrants in terms of what the signs of x and y are help us understand the relationship between the parameters at that specific point. Now, when we look at the linear equation, we have 4 letters here, y, m, x, and b. Y and x are our variables. M and b are our constants. So let's focus on the variables first. Y, that vertical axis, is our dependent variable. It depends on the values of m, x, and b. That's why it's on this left side here. X, this is our horizontal axis. This is our independent variable. We get to define the points here, and the values of m and b will then define the value of y that corresponds with that point x. What are m and b? M is our slope, b is our y-intercept. So m as our slope is defined as the rise over run, or delta y over delta x. You think of this as the change in y over the change in x between 2 points. So I'll give you an example here. So let's say, I'm going to try to draw this as straight as I can. Let's say this is my straight line. And you can pick 2 points. It doesn't matter what 2 points. If I know the change in y between those 2 points and the change in x, I can define my slope. Now you have to be careful what the sign is, meaning is it positive or negative change. So from this point to this point, there's a positive change in y. From this point to this point, there's a positive change in x. If there's a negative change in either direction, you need to account for it, or else your slope will not properly define what's showing up here, right? So here we have a positive slope. The y-intercept is literally the intersection between the line that we drew and the y-axis. So that tells us when x is equal to 0. So for this line that I drew, intercept is right there. In this case, b is equal to 4. Now, like I said, the slope, you have to know which sign. So this slope here is a positive slope. If I drew another line, let's say, pick this line here. Now, if you imagine you're a little person that's walking on the line from x equals 0, this point here, that intercept, and marching in this direction, you're going uphill, so positive slope. If instead you're marching on this line in the positive x direction, you're going downhill, so this is a negative slope. So the value of the green line, the m value of the green line would be a negative number. The value of the red line slope, m, would be a positive value. Take a look at these 4 linear equations. They're all of the form y equals mx plus b. Think about what the slope for each of these are and what the y-intercept of each of these 4 are. And pull out a graph piece of paper and pause this video and try to sketch out each of these 4 on a -10 to 10 x and y axis graph. Hopefully you're able to graph these 4 lines on your graphing piece of paper. If you ever struggle with these graphs, you can always use the free graphing calculator, Desmos, and compare to see if your graph is consistent. So let's take a look at this first line, y equals x. This has a positive slope, right? As you recognize here, right? Remember, if you start at x equals 0 and you move in the x direction, you're climbing this hill, so that's a positive slope. The y-intercept is equal to 0, because b term is equal to 0. So that's represented by this line crossing at the 0 point. And let's check, is a slope equal to 1? M equals 1 here. So the rise over run should equal 1. So the rise, in this case, if I look at this point and this point here, the rise would be 5. The run is 5. 5 over 5 is 1. Let's take a look at this blue line. Y equals negative x. That's this line right here. The y-intercept is 0. It crosses the 0 point. That's correct. We have a negative slope. If I start here, I'm going downhill. That is a negative slope. Is it a negative slope in equal to 1? Let's check. Well, if I go from this point, negative 5, 5, to the origin, 0, 0, my rise is a negative 5. My run is a positive 5. So that is a negative 1. And so you can do something similar to each of these, right? So let's look at this. Take a look at this green one. Y equals 2x plus 4. So where's my green line? Green line's here. So the y-intercept is 4. So it crosses at the 4 location. And the rise over run should equal 2. So this is a steeper line. It is a positive, so it's in, right? You're walking up the hill still. So let's take a look from this point. So if I cross here, so this is a rise of 1, 2, 3, 4, and a run of 1, 2. So 4 over 2, that is 2. That's a slope of positive 2. Finally, we look at this purple line. We have a negative slope, negative 5. So it's even steeper, but in the negative direction. And the y-intercept is negative 3, which it crosses right there, negative 3. So you can see how the change in slope and the change in the y-intercept affect the drawing of your line. As a point of comparison, here are 4 commonly used equations that are not linear equations. Remember, linear equations are that straight line that is described by y equals mx plus b. We have graphs that are like some type of natural log. We have a parabolic shape. We have trig functions like a sine curve. And then we have exponential growth, or I could have drawn an exponential decay as well. So this is a point of comparison to a linear equation where all the lines are straight. We'll see in future videos how these are used together and when these equations will show up in engineering applications as well. So if we have a positive slope, we're moving from the x direction and we're going up the hill. If we had a negative slope, we're moving from the positive x direction, moving down the hill. What happens if we have a slope of 0? Slope of 0 represents a horizontal line. If we plug into this equation y equals mx plus b, we see that horizontal line, or a slope of 0, represents y is equal to the y-intercepts. So for example, y equals 2, this will be the horizontal line. Rise over run is a slope, remember. The rise is 0, so rise over run will always be 0. Here's another example of another one, y equals 8. So any horizontal line has a slope of 0. What happens if we draw a vertical line? Then the run is equal to 0. So rise over run, if you have something over 0, it will be infinite. So a vertical line has a slope of infinity. So as an example, x equals 2. You would not use the y equals mx plus b form if you're drawing a vertical line. One interesting way to look at how the y-intercept affects the graph is to pick 2 lines that have the same slope and change the y-intercept. So as an example, let's say that the slope is equal to 1. So then my equation y equals mx plus b simplifies to y equals x plus b. So if I graph, pull out a graph paper and follow along, graph y equals x plus 2, my slope is 1. You can check that comparing the rise and run in a graphing paper. If the grids are square, you'll see this represented by crossing the diagonal corners. And the y-intercept is equal to 2, so it crosses the x equals 0, y equals 2 point. When you have 2 lines of the same slope, you're going to have parallel lines. So the y equals x plus 8 graph should cross at x equals 0, y equals 8, that's the y-intercept, and be parallel to this red line. And that's what you see here. These 2 lines are parallel. They will never cross. We can take a look at another example with a slope of negative 2. So our equation now simplifies to y equals negative 2x plus b. Let's pick a y-intercept of 4. See if you can graph this one. So you have a negative slope, so it's going to go in this direction, and it's going to intercept the y-axis at y equals 4, so right there. So there's your y equals negative 2x plus 4, and let's graph one more line that's parallel to this one, so I'll choose slope of negative 2 as well, and choose a different y-intercept, in this case negative 5, and there's my line, right? So really important concepts here. When the slopes are the same, the lines are parallel if it's a linear equation. As you change the y-intercept, you're just shifting, offsetting the graph by that value. Now, when do we actually use linear equations in real life? There's two main scenarios that I can think of. One is when there's a relationship between two parameters that you can describe as linear. And the second is the physical case, when you physically see a straight line in a system and you want to understand that relationship better. So the simplest one I can think of is a ladder leaning against a wall. Now, whenever you are trying to use these equations, you need to find where your 0, 0 point, your origin, right? So if I have a ladder leaning against a wall, I would probably define the origin as the base of where the ladder is touching the floor. And then that means the y-intercept would be 0 there. Then you would measure and you could figure out the slope, m value, and then at any given rung, if you measure the distance along the floor, that will be the x value, you could use the equation to predict what the height at that rung would be. And then you can measure the distance from the base of the ladder to the wall, and then you could measure how high the ladder can actually reach. Similarly, you can look at the slope of a hill. Inclines are defined by the slope, the rise over run. But a lot of times we're not trying to just look at a physical x position and y position, relate those. We have other things we want to look at. So another common comparison is some parameter x to time. Now, our vertical axis in the past was a y variable. Well, these are interchangeable. I could change this to a temperature. I can change this into a force. It really doesn't matter. It's up to us what application we want to use it for. And here we change this one to a time value. Now, the horizontal axis would remain your independent variable, and your vertical axis would remain your dependent variable. So in a case like this, you might look at a toy car and you want to look at the position as it moves along. You would make a lot of assumptions if you actually say that it's a linear, it's modeled as a linear equation. One of the major assumptions you would make is that the speed or the velocity throughout this path is remain constant and it's staying all along a single line. So let's say you know the starting point, you start a timer and you measure 20 seconds and you measure how far it's traveled, and it traveled 6 inches or however far it might have. And then you can draw a line between these 2 points. And if it truly is a constant speed, then this line would represent the path of this car. Now, in addition, you might use it for linear interpolation, and we'll do a whole another set of videos for each of these different cases. Linear interpolation is used a lot in a thermodynamics course, where you have a lot of tables of material properties or gas properties. So linear interpolation is used if you have a table that represents the relationship between temperature and some thermodynamic property. But because it's a table and not a graph, there are discrete points. So they might have the temperature at 100 degrees, at 120 degrees, but not at 110 degrees. So you would need to linearly interpolate using the values that are given that are just above and just below, making the assumption that you have a linear relationship between those 2 points. Equipment and sensors often are calibrated using a linear approximation, at least in small ranges. So what does this mean? This means that, let's say that you have a thermocouple, a way to measure temperature. The sensor itself will generally needs to be calibrated unless you have a handheld system that already calibrates for you. So a lot of times it does, but you want to check that. So you would need 2 points. So the temperature measuring tool that's often used is measuring at boiling water and measuring in an ice bath. So you know 0 degrees and you know 100 degrees Celsius are 2 good reference points. And you take the raw data from the sensor and you use this simple equation y equals mx plus b to help calibrate. So at any other temperature, you would do a direct relationship with the calibration curve and find out what the tool is actually measuring, what temperature that's actually measuring. And lastly, linear curve fits. So let's say you run an experiment, you have a variety of data points, and you want to describe what the behavior of the data that you observe is. You can describe it by a table of all those points, but if they lie nicely along a line, then we can use linear curve fit and give an equation that fits the data well and describe the experimental results by that equation. So each of these different areas of application will have another set of videos that could dive deeper into it, and you'll see the actual use that you will actually use it for in an engineering class in the future or engineering projects.